Correct.
All right. So, yeah, so what Ms. Rahman asked is like the major question of this whole thing, right? So let's talk about this equation right here. First of all, you need to understand the context. This equation is applicable when you have a charged particle. So proton, electron, ion, something like that, something that's charged. And that charged particle is moving through a magnetic field. That is the only time you will get a force acting on that particle, a magnetic force. That's what this equation is used for. It helps you find the size, the magnitude of the force that the charged particle feels when it's moving through a magnetic field. Does that make sense? That's what this equation is used for. So pretty simple. You have to have a particle that is charged. You have to have a Q. You have to have a charge in the field. It has to be moving. In other words, if the velocity is 0, if the particle is just sitting there, oddly enough, the field, the magnetic field does not exert a force on it. And then finally, your charged particle has to be moving through a magnetic field, which we denote with B. So these are just variables in an equation. And this simplifies then to an equation that would give you the size and the strength of the force that the magnetic field exerts on the charged particle. Okay, remember that forces are always measured in newtons. So this is just like a normal force, like we've always been talking about. Who can tell me what's special about that X symbol?
It's a dot product.
Cross product.
Cross product, because it's really an X.
Cross, yeah.
Yes.
Raw product.
Yes, wrong product. Oops.
Ultimate pin.
Okay. So let me see if I can write this. Yeah. So, oh boy. Why is it not working? Oh, my tablet is not plugged into my computer. Okay. All right. So let's talk real quick about what a cross product is and how it works. So the cross product cares all about the component of the two vectors that are perpendicular to each other. In other words, that like don't agree in terms of their direction. So hold on, someone's trying to get in. Osborne is here. Okay. So a cross product is all about the perpendicular component of the two vectors. So to think about a cross product, so let's say that I have a magnetic field, and again, I did a video like this, or an example like this in the video. Say I have a magnetic field B, it's moving to the right on my page, and let's say that I have a charged particle, let's make it positively charged, and it's moving with some velocity up like that. So up at an angle through my magnetic field. The cross product of those two vectors can be found in this way. You draw the two vectors that are acting on the particle tail to tail. So here's my vector B, the field that the particle is in. Here's my vector V, the velocity of the particle. And I need to think about the angle between those two vectors, the angle theta. The cross product of these two vectors is V cross B. And the size of that will be VB times the sine of the angle between them. So you need to understand what this means and how it works. Of course, the sine of theta has a range from 0 to 1, right? So if my two vectors were perfectly perpendicular, the angle between them would be 90 degrees, and VB would have its maximum value. It would be V times B times 1. If my two vectors were parallel to each other, then the sine of that angle would be 0, because the angle is 0. They have no angle between them. So if my two vectors were parallel, then their cross product would be equal to 0. If I'm somewhere between parallel and perpendicular, like I am in this example problem, then I would have to pause and multiply V, multiply B, and pause to calculate the sine of the angle between the two vectors when they're drawn tail to tail. Just like that, okay? So a cross product, you just multiply the two together, the sizes, and then you kind of adjust it by a factor of the sine of the angle between them. So that's how a cross product works. So if you're asked to actually calculate this, then it's going to be QVB sine theta, where you all need to understand that that theta is the angle between the two vectors when you draw them tail to tail. Okay? So let's talk about this statement here. This magnetic force is only going to cause the particle's velocity to change direction, but not magnitude. So, Ms. Rahman, this is a question you were asking. The reason is that this force will always end up perfectly perpendicular to the velocity. So this will always be true. And you guys need to be clear on this. The magnetic force that results from a charged particle moving in a magnetic field will always, 100% of the time, be perpendicular to that velocity vector. In fact, the magnetic force is perpendicular to both the velocity vector and the field vector. It's perpendicular to both of them. Mr. Moore, yeah, we're going over the notes right now, and then I'm going to work some example problems. Okay, so we know that the magnetic force is perpendicular to both of these things, and we have like two options for that. So think about this. Right now in this example problem, my velocity and my field are both in the plane of the screen. And the only option for something perpendicular to that would be something coming out of the screen or something going into the screen, right? So this is where the right-hand rule comes into play to figure out the direction of this force. To figure out the direction of the force on a positive particle, you have to take your right hand, you have to line it up, align the fingers of your right hand up with the velocity, and then you have to figure out how to turn your hand. Did you play anything?
Yeah.
Great job. Why don't you go read some books, and after you've read some books, you can do. You have to figure out how to turn your hand so that you can curl your fingers as if you were swinging that.
How much?
Go read 3 books, okay? So that you can swing the velocity vector onto the B vector, and that's the direction that you need to be able to curl your fingers. So in this example problem, you can see the velocity vector is up and to the right, but I need to turn my hand so that I can curl the fingers of my right hand in the direction that I would need to swing the velocity vector, so it would line up with the B vector through the smallest angle possible. So if I hold my hand like this with my thumb pointing to me, that's the wrong way. I need to hold my hand like this, point the fingers of my right hand up to that velocity vector, and now I'm able to curl my fingers and swing them down towards that B vector, and that has my thumb pointing into the screen. So I know that this magnetic force vector is going to be pointing into the screen, and we always denote that with an X because it's like you've shot an arrow and you're looking at the tail feathers of that arrow, so to speak. Does that make sense? So you guys have got to be able to use the right-hand rule to figure out the direction of the force. And it is kind of tricky, and I actually made a mistake on my video that we need to go over in 1 second. Well, let me think about this.
Was it the mistake that you corrected, or?
No, there was another one.
Yeah, I was thinking that too when you were talking about it.
Yeah, I made a mistake on the.
I corrected it, don't worry.
Yeah, Mr. Moore, he got my back. Okay, so it's one thing for you to understand the direction of the force. It's another thing for you to understand what result that has. So we need to talk about forces and have kind of like a little kinematics and forces review. What do forces cause? What do unbalanced forces cause?
Acceleration.
An acceleration, excellent. A change in velocity. So a change in velocity can mean 2 different things. It can mean that the velocity is changing size, is growing or shrinking, in which case the particle would be speeding up or slowing down. The only way, for example, for this velocity to change its size is if I had an acceleration vector that agreed with it. In other words, if acceleration is the change in velocity, if I'm going to change the length of this velocity arrow, if I'm going to change the size of the vector, I would have to have some acceleration in the same direction as it. Does that make sense to everybody? That's the only way I can grow or shrink the velocity vector, to change the speed of the particle. But I don't have a force that has any agreement with the velocity. The force that I have right now, the magnetic force coming from this field, is always perpendicular to the velocity. So these accelerations don't exist right now. The only acceleration I have, we just decided that that my force vector is going into the screen. That's perpendicular to the velocity vector. So that's going to be my acceleration vector as well, going into the screen. That's perfectly perpendicular to the plane of the screen where the velocity is. So my particle will never be sped up or slowed down by a magnetic force like this. Rather, it's only going to change direction. So if this particle was actually flying through this field like this, it would experience a force towards the screen. My particle is going to start curving towards the screen. Does that make sense to everybody?
Yep.
Kinda. You with me?
Yep.
Okay. So let me go find the mistake I made, and we can practice some right-hand rule stuff together. I think it was this one where I messed up. So I think in the video I said up and to the right, but I had it opposite. So let's go over this one real quick, and you guys can practice the right-hand rule. I'm kind of working backwards here because now I know what the magnetic force is. So that's the direction that my thumb has to point. And this is a positively charged particle. And the velocity v is directed into the page. I think when I was doing the video, I misread this as coming out of the page. So I need to take my right hand. I need to point my fingers into the page because my fingers have to line up with the velocity vector. I know that the force ends up pointing up and to the left like this, so my thumb has to be pointing up and to the left like this. My fingers on my right hand are pointing into the screen, and then they're going to curl as if I'm swinging that velocity vector down to like meet the field vector. So when I do that, my fingers are curling down and to the left right now. And so the answer should be E. I had it backwards. I think I had the velocity coming out of the screen. So yeah, please note if you were taking notes and doing this example problem with me in the video, the answer is actually E. Does that make sense to everybody? Are we good with that? Okay. So again, it's one thing to understand the right-hand rule and be able to think about direction of forces and velocity and the field vector. It's going to be another thing for you to understand what the particle is actually going to do as a result of that. So let's do some practice problems with that, and then we'll be done. Any questions about the PowerPoint?
I do have a question.
Yes.
Okay, so I don't know where this was in the PowerPoint, but in my notes I wrote a force perpendicular to velocity causes an acceleration perpendicular to velocity, which only causes a direction change.
Yeah.
That's still kind of confusing me.
Okay. So that's kind of what I was getting at earlier.
Yeah.
The only way for velocity, so let's say this is a velocity vector. The only way I can grow that or shrink that is if I have a change in velocity, which is acceleration, that agrees, that's in the same direction. In other words, let's say that my acceleration vector looked like this. And let's say this is like my velocity at time 1. My velocity at time 2 would be my old velocity plus the change in velocity. So my velocity just got bigger. I just sped up. The only way I can speed up or slow down like that is if acceleration has some component like this that is parallel to, that agrees with the direction of velocity.
But the acceleration's always perpendicular?
Exactly correct,
Okay.
because the force is always going to be perpendicular to velocity. The magnetic force will always be perpendicular to the velocity vector of the moving particle.
You said always, and then you like corrected yourself in the video saying like most of the time. What's a case where it won't?
Did I?
Yeah, I think you said like always, and then you're like, well, I'll say for the most part. I didn't know if there was some like special case.
So yeah, we're dealing right now with point particles, like point charges.
Yeah.
And later we are going to be looking at extended charged objects like wires or loops of
Oh,
wire.
okay.
And in that case, it's going to be more complicated.
Okay.
Mr. Thurman?
One second. All right, dude, you can get the switch. Okay.
How much time?
Oh, 15 minutes? Yes.
Okay, so how would the perpendicular acceleration cause a direction change?
So just like this. So we know that this is not happening. So let's say that here's my first velocity at time 1, and then here's my change in velocity, my acceleration, which is perpendicular to that.
Mm-hmm.
So what's my new velocity going to be like? It's going to be the same size, but it's going to be shifted up a little bit.
Oh,
Because
Got it.
it's just like I'm adding these vectors. If this is my old velocity vector, this is a change. Initial plus change equals final, right?
Mhm.
Does that make sense?
yes. Thank you.
It's important to note, though, that, and this is really key, that if my velocity is changing direction, then we've just said that force is always perpendicular to velocity. So in the next instant, my force is going to be pointing in a new direction. Like, in other words, it was perpendicular to my old velocity, but I just had a change in velocity. So that's no longer the direction of acceleration and force. My new acceleration will be like this way. And so you end up getting like your magnetic force is going to be continuously changing direction because the
In a parabolic path or
Well,
or something?
circular.
Parabolic or circular?
Yes, exactly.
Yeah.
Yep.
All right.
With the velocity of the particle, right? It's gonna
Yes.
change as that changes.
Yep.
Depending on how long the force is?
Yeah. So if we do some example problems,
Is there a relationship like with time that is like
so not one that you're going to have to think about like explicitly, but
okay.
just kind of more in a general sense. Like, in other words, it does depend on how long the particle is traveling through the magnetic field. Like, how long is that changing force applied to the particle? If it's just applied for a short amount of time, then maybe the particle will, just start to sweep out a circle, and then it exits the magnetic field, and then it's going to continue on in that parabolic trajectory, if that makes sense. If it's in the field for a long enough period of time, then it could be moving. I posted a reading about this if you guys care about it. It could be moving in like a helix. It could be spiraling. Or depending on the direction of the field vector, it could be moving in a circle. So really, you're not going to have to think about like it's going to be pretty clear to you in any problems what the path is going to be.
All right.
Okay. I think there was maybe some example problems in the PowerPoint where I was going through the possible paths.
Yeah.
Okay. Did you guys understand what I was saying with work? That magnetic forces can never do work
Yeah,
on a
no
charged
work.
particle?
Your screen's being really weird right
Yeah,
now.
that's really. I'm so glad that's like something easy to know about magnetism. Just be like, okay, there's no work.
Yes, it's nice.
Instead of having to do some big calculus, that's just that's nice to know.
Did someone say my screen is messing up?
Yeah, it's like the bottom right corner has like frozen, I think.
Hmm.
It's good for me.
Over here.
Yeah, I don't see that.
Okay. Well.
Maybe it's just me then. Okay.
Sorry, Mr. Hoffman. Okay, let's do some practice problems. So hopefully you guys looked at some of these. If not, that's okay. So this is question 1, and I had 2 questions. So let's just go over the 2 questions as quickly as we can, and then we'll be done.
Are we gonna
All right.
have anything to do tonight?
No.
Sweet.
If you already turned in the notes that I asked.
Awesome.
Yep. Okay, so we have a charged particle. It's being shot out of this radioactive source with some velocity, and then it enters this region that is called region 1. I have two things happening in region 1, don't I? I have a magnetic field coming out of the page towards me. That's what those little dots represent. And then I'm also going to have an electric field. And they were kind enough in this question to tell you that. And of course, the electric field is directed up from positive to negative, right? So this particle is going to be under the influence of two different forces. There's going to be a magnetic force due to the magnetic field and an electric force due to the electric field. Okay, so it's saying that this thing is a velocity selector because only particles moving with a certain velocity will move in a straight line through this path. Can someone explain why that's true?
Could you say that again? Sorry.
Yeah, only particles moving with a certain precise speed or velocity will be moving through with a straight line through this region. Any other particle moving with a different velocity will not. Can someone?
So the force of magnetism cancels out with the electric force.
Yeah.
Exactly. The only way that this thing can move in a straight line is if there's no net force on it to cause a direction change, to cause an acceleration, right? As it moves through here, it's positively charged. We know it wants to follow the electric field. It wants to go away from the positive plate towards the negative plate. It wants to move curling up towards the top of the page. If the magnetic force can counteract that, and we know that the magnetic force depends on the velocity, then it's going to move in a straight line. And that's what it's getting us to think about here in part 1 of the question. So in part 1, I want to derive an equation for the speed of the particles that do move in a straight line. So we've already thought about what is going to be true for the particle to move in a straight line in here. The forces up and down have to be equal to it, right? So I'm going to draw a free body diagram to think about this. I know I need to analyze forces because when it's traveling through this region, I know there's going to be an upward force on it. So I'm thinking, okay, what's the only way that it can travel in a straight line? Oh, if there's a downward force to cancel out that upward force. So here's my particle. It's positively charged, and I know that it's moving with a velocity of v. So I'm going to add that to my diagram. And I know that it's going to have an electric force pointing up, following the field, right, from positive to negative. And then I know that the magnetic force has got to be pointing down. I know that because of the right-hand rule. So if the velocity is this way, and the magnetic field is coming out of the page, and I curl my fingers towards me out of the page, my thumb is pointing down right now. So according to the right-hand rule, the magnetic force has got to be pointing down. I know that these two forces then have got to be equal to each other for this particle to move in a straight line. So all I have to do is write expressions that set them equal to each other. Someone tell me the expression for the electric force of a particle moving in a uniform field. And they're letting us use E, capital E, which is the sign for field.
Capital E times
EQ.
Exactly, yeah, EQ. So remember that we define the field as a force divided out by the test charge. So we haven't seen this in a long time. Therefore, field times test charge will equal the electric force, right? So that's going to equal EQ. And my magnetic force, of course, equals Q times V cross B. And that simplifies to QVB sine theta, where sine theta is the angle between the velocity vector and the field vector. Well, I've already thought through the fact that the velocity vector is pointed towards the right. The field vector is coming out of the screen towards me. That's a right angle. So the angle theta between the velocity and the field vector, this should be B1. The angle between them is 90. The sine of 90 is 1. So, and again, I know these are equal to each other. So I can set them equal. EQ equals QV B1. Sine of theta, sine of 90 is 1. Now I just have to rearrange this and I'll get this. So that's not too bad.
Wait, Mr. Thurman,
Yes.
is a cross product not the same thing as a dot product?
Dot products are different. Dot products, so a cross product is worried about how the particles are perpendicular to each other. A dot product worries about how they are parallel to each other. If you have,
Oh,
if you have a
okay.
dot product, like work is the integral of force as a dot product of displacement, for example.
It's how much agrees with it.
Yeah, so that ends up being F cosine
Cosine?
theta dx. Yeah, we're worried about the cosine of the angle between the two vectors. That's a dot product.
Okay.
Okay. All right. Let's see. Part B. Some particles are emitted from the source with speeds greater than this. Which of the following describes the initial path of one of these particles after entering this region? So first of all, I know that they're only going to move in straight lines if they have this velocity. If the velocity is bigger than that, let me draw a free body diagram again, then is my electric force going to change at all? No, it's going to stay what it was before, Q times big E. The electric force has nothing to do with the speed of the particle. What will change?
Magnetic force.
The magnetic force is now bigger than the electric force because my velocity is bigger and the magnetic force depends on the velocity, right? So my magnetic force is bigger. So right when the particle enters this region, it has a net force down. In other words, it's moving to the right, but it has an acceleration pointing downward. That's just like projectile motion. It's going to curl in this path down to the bottom of the page. So that is the answer. It curves to the bottom of the page. And our explanation there is that bigger velocity means bigger magnetic force pointing down. Okay. A constant magnetic field of B2 is now directed into the page in this region. So let's say that we have this particle traveling in a straight line and it enters region 2. And then I want to try to derive some expressions. So determine expression for the initial magnetic force on the particle in region 2. So this should not be too bad. I know that magnetic force is QV V cross B, which is QVB sine of theta. And right here, the particle is entering this region with a velocity to the right, and the magnetic force is going into the page now. So right hand rule, my fingers of my right hand going to the right, aligned with the velocity. My fingers curl towards the screen, into the direction of the field vector. So now the force is up in this region. That makes sense. In the last region, region 1, the force was down because the field was going into the page. Now it's up because no, I'm sorry. It was down because the field was coming out of the page, and now it's up because the field is going into the page. Anyway, the velocity and field vector are still perpendicular to each other. So the sine of the angle between them is still a 1. Is everyone clear on that? If my velocity is this way, my field is this way into the screen, then that's still a 90-degree angle. So I know that the magnetic force in region 2 is going to be equal to this. And again, that simplifies to QVB, and this is B2 because I'm in this second region. And we have an expression for V. Notice they don't tell us that we can use V, but earlier didn't we not show that V is equal to E over B1? So we can just plug that in here. So my magnetic force ends up being Q E B2 over B1. Once again, we have to state its direction. It is directed up because of the right-hand rule. Questions about that? Okay. Describe the changes in the magnitude and direction of the magnetic force as the particle moves in region 2. So this is a really important question. So we said that initially the particle has this velocity right here, and the magnetic force is up. So that means that the particle is going to accelerate upward. which means that the next instant, its velocity is now going to be same size, but a different direction. Well, now which way is the force going to point, the magnetic force going to point? The magnetic force is going to get tilted as well, because the magnetic force is going to be governed by the right-hand rule. So if my velocity is up like that, then my force is going to be up and to the right, up and to the left as well. And you can see if we keep thinking through this, that based on this acceleration, my new velocity is going to tilt to the left some even more, and then the force will be pointing this way. We're going to get circular motion. We have a force that's always pointing into the center of the circle. So for those of you who don't remember this from general physics, this is important. For something to move in a circle, circular motion, we have got to have a net center-seeking force. What word do we give to that force?
Centripetal.
Yeah, we call it a centripetal or radial force. It's not a real force. It's not a force that you will draw on a free body diagram. Rather, it comes from other forces. So in this case, I would say that the magnetic force is supplying a centripetal force. Does that make sense? Because it's always pointing into the middle. So part C and D, these questions kind of go together. Describe the changes in the magnitude and direction of the magnetic force as the particle moves in region 2. The force is going to be changing its direction to always remain perpendicular to the velocity. And the velocity is changing direction because of that force. So they kind of influence each other. The force causes the velocity to change direction, which causes the force to change direction, which causes the velocity to change direction, etc. And the path it's going to take is going to be purely circular. Now listen, you will always have your particle undergoing circular motion if the velocity vector and the field vector are perpendicular to each other. That is always the case here. And as long as you have no other forces acting. Over here, I didn't have circular motion because I had another force to counteract the magnetic force. I had the electric force, right? Over here, though, I don't have anything to counteract it. So my velocity is always perpendicular to the field. The field is going into the page at all times, and my velocity is in the plane of the page. That's always perpendicular. So you will always, always, always get circular motion whenever your velocity vector of the particle moving through the field is perpendicular to the field. That will always result in circular motion.
So like when would there be like a parabolic path, like you said in the PowerPoint?
So it's going to be, I guess, in a situation like this, this is going to be a bit difficult to draw, but kind of a situation that I drew at the beginning where here's my field, maybe going to the right, and maybe I have a particle that is going like this way in the field, then those are not perpendicular to each other, and the force is going to cause this thing to like spiral or do a parabola or something like that. Yeah. Okay. Let's see. Okay, part E is a really important question. Derive an expression for
Really important.
derive an expression for the charge to mass ratio of the particle. Okay, so where am I going to get mass from? Well, we've just said that the magnetic force in that second region is supplying a centripetal force. So we just said that the magnetic force, this was the answer to part B, I think, is Q E B2 over B1. That's what we proved earlier. And I just got done saying that in region 2, this magnetic force is supplying a centripetal force, which causes centripetal acceleration. So that's the only force acting on the particle. So according to Newton's second law, that's going to be equal to the mass of the particle times acceleration. But note what I just said about this acceleration. It is a centripetal acceleration. It always points into the center of that circular path. So my particle is moving in a circle right now. the force we just proved is always going to be pointing into the center of the path. And that's the only force acting. So therefore, I also will always have an acceleration pointing in that same direction. And an acceleration that points towards the center of the circular path is called a radial acceleration, or a centripetal acceleration. So I could call this radial or centripetal acceleration. Does anyone know from general physics the equation for radial acceleration of a particle moving in a circle?
Isn't
V
it
squared over T.
V squared over R,
R?
where
R,
R is
yeah,
the
R.
radius. R is the radius of the circular path. Okay, so the equation becomes this. Let me neaten this up a little bit. I now know that the magnetic force, which I derived in part B as Q E B2 over B1, that is my centripetal force, which has to equal m times the centripetal acceleration, right? And remember that this velocity was given to me earlier. I proved that, like, that was the first question right away. That velocity was E over B1. So you have to get used to this. Sometimes you have to go digging in previous parts of the problem to try to put things in acceptable terms. This velocity is the velocity that the particle had leaving region 1 and entering region 2. It's the same size of velocity. And we said earlier that it was E over B1. So I'm going to get E over B1 squared right here. And now all you have to do is rearrange this so that you get Q over M, and that's it. And the only thing that we're introducing new here is R, where R is the radius of the circular path. I'll leave the algebra up to you guys, but you end up getting this. Q over M equals E over B1, B2 times R. How do we feel about this first question? Feel okay? Are there any questions? Hey?
Could you like maybe go back to E over V1 squared?
E over V1. Oh, so this is just that's just the velocity from part A.
Oh, okay.
Yep. All right, let's do question 2. This one was trickier. Okay, so here's the idea behind this question. This whole box is shaded, and they're telling me that in the shaded region, so throughout the entire thing, there is a magnetic field perpendicular to the page. So either coming out of the page or into the page. They don't tell me. So this arrow is tracing out the trajectory of a charged particle. So my charged particle is moving in a straight line here, because within this region, what else is influencing the particle besides the magnetic field in this region? Anybody? What? Nobody knows. So these are like charged plates. They have a voltage difference supplied across them from here to here. So if these plates are charged, what must there be in this region?
Field.
An electric field, okay? So just kind of similar to the last problem, I have an electric field in this region and a magnetic field in this region. They must be canceling each other out to keep the particle moving in a straight line. Does that make sense? Mm-hmm. Okay. So part A, I want to know in what direction should the magnetic field point? Well, we have a 50-50 chance. I know it has to be pointing out of the page towards me or into the page away from me. How can I figure this out? Well, let me find the simplest portion of this to analyze where the particle is just under the influence of that field. That's this region, right? When it comes out of this electrified tunnel, here the particle is just under the influence of the magnetic force. So this is the trajectory it's taking. If you guys are not familiar with this from general physics, the velocity of a particle taking a curved path is always instantaneously tangential to the path. So in other words, the velocity right here is this way. The velocity right here is tangent to the curve. The velocity right here is tangent to the curve. Is everyone kind of familiar with that idea? So these are the velocity vectors. Your velocity vector will always be, your velocity vector at that instant will be tangent to the curve path at that instant. So I can just pick one of these and use it to help me figure out the direction of the field, because this is circular motion, isn't it? Right here. So which direction is the force pointing, the magnetic force?
Towards this, or whatever, in the direction of the radius.
In towards the center of the circle, exactly. So here's the magnetic force here. It would be right here. So my magnetic force is always pointing into the center of the circle. So I can just pick one of these then and use the right hand rule real quick. I'm gonna look at this bottom one. It really doesn't matter. Point my fingers in the direction of the velocity so that my thumb can point up in the direction of the magnetic force. Which way does the field have to be going? Into the page, into the screen, because that's the way my fingers are curling as my thumb points up right there. We could do it also with any of these. If I chose to do it to analyze this pair of vectors over here, I need to somehow point my my fingers in my right hand with that velocity, so my thumb is pointing in the direction of the force, and my fingers are curling into the page. So your answer there, I don't think they're going to let you write into the page because they explicitly said to use the reference system that they've set up. Positive z-axis is out of the page, so the answer to question A would be along the negative z-axis. And then you could say into the page if you really wanted to. But does everyone understand how I figured that out? I looked to see where the particle is just under the influence of that field. And I know that that's here. I see it's in circular motion. I know that the velocity vector is always tangent to the path. I know the force vector is always into the center of the path. By finding a pair of vectors to analyze, I can figure out the direction of the field. Okay? Part B kind of rests on the fact that you figured out part A. So I know that when the velocity vector is straight down, the magnetic force vector is to the right. So in this region here, for the particle to not be following a curved path, I know that I have to have a magnetic force vector to the right, and therefore I need the electric force vector in this region to be pointing to the left. What charge then should I give plate K to make that true? Hi, Ms. Batson. We're just going over the example problems that I posted.
Okay, awesome.
So if I know that in here the magnetic force is pointing to the right, to keep the particle going in a straight line, I need the electric force pointing to the left. So can someone tell me what charge I should give to plate K? Positive or negative?
Negative. Or sorry, positive.
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 Yeah,
negative.
positive. Because remember, guys, I need the electric force. These are positively charged ions. I need the electric force to be pointing to the left. For a positive particle, that's going to agree with the way the field points, and field always points from positive to negative. So I need the field to point that way. So K has got to be a negative, K has got to be positively charged as well. This is something I did not mention. I failed to mention this. You really need to pay attention to whether your particle is positive or negative. Who can tell me why? For all this magnetic stuff.
Because
The magnetic
negative
force
right
is
hand
like
rule is
up.
opposite.
Yeah.
Yeah, it flips, right? So if I was looking at a negatively charged particle, then this would be incorrect. My magnetic force would be pointing the other way. Mr. Wisdom asked me if you could use your left hand for negatively
That's
charged
what I was
particle.
thinking. But I
Yeah.
don't think it works.
I think that you can. I haven't really tried it. Do you guys? What do you think?
Wait, I think I tried it, and well, maybe it does work. Oh yeah, I guess so. Yeah, because you're gonna, if you flip your,
Yes.
You flip your
Yeah.
hand over to where your fingers curl in the same direction. Your
Yeah.
thumbs can be pointing
Yeah.
forward.
Yeah. It should work for a left hand. Okay. Question C. Calculate the magnitude of the electric field between the plates. That's pretty simple. Here's an equation we haven't seen in a long time. The voltage, the potential difference across two parallel plates where the field is uniform between them is equal to that field times the distance, isn't it? So I know the voltage, I know the distance, therefore I could calculate what the field is. So that's going to be pretty simple. I'm just going to go over these pretty quickly now. So we've done A, we've done B, we've done C. Question D, calculate the speed of the particle that can pass between the plates without being deflected. Anyone know what I'm going to do to solve question D? Again, I'm looking right here. I want the thing to travel in a straight line. So what has to be true for the thing to travel in a straight line?
Force is
They
gonna
have
be
to
equal.
agree.
The forces have to agree with each other, don't they? So this is very similar to a problem that we've already seen in the last practice. I know the electric force is Q times E, and in part C, I just calculated what that field is. And so now I'm going to set that equal to the magnetic force, which is Q V cross B, and V cross B is V B sine theta, where that angle theta is the angle between the two vectors. The field vector is always pointing into the page. So of course, that is 90 degrees.
Daddy, I have a quick question.
What's up, Ben?
Why a minute ago did I see Ganon's evil sparks here?
I have no idea, dude. So then we could calculate the speed of the particle for which that will be true. Okay. Part E, where am I going to get mass from?
MV squared of R.
Yeah, so that's the circular motion thing again. So I know that down here, my magnetic force, which I know is QVB, and I've already found what the velocity is in part D. That velocity can't change size, so that velocity is going to be the same in part E as it was in part D. And I know that's supplying the centripetal force, isn't it? The force that's always pointing into the middle of the circle. So that's going to be m times centripetal acceleration or radial acceleration. And I know that radial acceleration is v squared over r. They've given me the radius. I know what b is. I figured out what v is. So I'll be able to calculate what the mass must be. I'm trying to figure out if I ever can cancel out the q.
Is that just a charge on a proton? Or?
Well, it says singly ionized, positively charged ions. So yeah, it must be the fundamental charge, the charge of a proton. Yes. Okay, I'm going through these kind of quick, but I can trust you guys to do the algebra. Part F, a doubly ionized positive ion. What does that mean?
A positive
Two
charge.
protons.
It has a charge of 2 protons, right? 2 positive, of the same mass and velocity as the singly charged ion enters the mass spectrometer. What's the new radius of its path? Okay, so the velocity is the same. The charge is now double, but the mass is the same. Yeah, so the only thing I'm changing is the charge Q right here. I'm doubling it. So if I take this equation and I double the left side and I keep everything else the same, what's going to happen to
R decreases.
do what?
R decreases.
D
Divided by 2.
Yes, that's correct. Yep, because I need if I multiply this side by 2, I've got to multiply this side by 2. And because radius is on the bottom, that's the same thing as me dividing the radius by 2. So the radius shrinks. That's correct. I think I mentioned this before. If everything else is the same, so my magnetic force is the centripetal force, and it's equal to QVB in this situation. And if my Q doubles, then my magnetic force doubles, and a stronger force is needed to turn tighter curves. So of course my radius will shrink by a factor of 2. And that makes sense conceptually and mathematically. So the new radius would just be what, 0.25 meters. Okay, so we've seen some practice multiple choice questions, one of which I corrected on the PowerPoint. We've seen these practice free responses. Any questions at all about the magnetic force acting on a charged particle moving through a magnetic field? Any questions about the right-hand rule? Any questions about circular motion? That's something that kind of got thrown in here, but it is important for you to understand. And a particle will move in a circle when it has a force that always changes direction to point in toward the center of the circle. Which
Here,
is,
I have a question.
yes.
So if the velocity was pointing, if like a piece of it was pointing into the screen, then would it be parabolic instead of circular?
Yeah, I think so. It'd be parabolic or helical at least,
Okay.
because yeah. So Mr. Prabhupada is getting at this thing that we've mentioned a few times. I'm gonna have to think through this to be better prepared to answer this after spring break. But he's saying that if the velocity was not in the plane of the screen, but some of it was pointing into the screen, like some of the velocity was pointing into the z-axis, then my field and my velocity are no longer perpendicular. And so I'm not going to have circular motion. I'm going to have something else. It's going to be like it's going to be parabolic or maybe helical, like a spiral. I need to think about that some more. I think that they're mainly going to stick with like having you figure out like what the path of the particle will be like right at the instant it starts to feel the force, or if the force, or if the field and the velocity are always perpendicular to each other. So once again, if the magnetic field and the velocity vector are always perpendicular, you will always have circular motion. As in this case and the case we looked at last time. Yeah. And please note that we've seen several instances of this where a particle can be under the influence of two different forces, a magnetic force and an electric force, and that can result in different paths, like a straight line path, if those forces balance out, etc. Okay, anything else that you guys need from me? So I'm sorry that we're starting this unit right before spring break, but we just have to keep on trucking in this class. So where we're going to go with this unit after you all come back for spring break is we're going to take all this and use integral calculus to figure out what happens when we're not just looking at a single charged particle in a field, in a magnetic field, but when we are looking at like an extension of charge moving through a field, like a wire or a loop of wire or some shaped object. And that's going to be a little bit more complicated. We're going to see what happens when you have a wire that is carrying current that is in the presence of a magnetic field. And then we're going to move on and see how charged particles moving, they themselves can generate magnetic fields. So that's going to be super fun. So I'll have all that ready for you guys after spring break. I don't know, obviously, I don't think we'll be back at school. So I guess just be watching your emails, watching the Google Classroom closer to the end of spring break to see what your instructions will be. Yeah, no clue. All right, y'all. Thank you guys for your time. Thanks for your patience as we try to figure stuff out this week. If you have any questions or need anything at all, please let me know, okay? And you guys try to have somewhat of a good break. Keep yourselves healthy. Don't go outside. I mean, go outside. Don't go into crowded places. Please get some sunshine. And wash.
It's not, or it was nice earlier.
What?
Now. It was nicer just a little bit earlier. It's still bright. But
I'm literally going to work
cloudy
after
now.
this. So.
Wash your hands, Mr. Bunnier.
No, thank you.
Can't wash your hands if you don't have hands.
Make sure to touch your face.
What?
Technically speaking, when you wash your hands, you're not doing anything. Your hands are washing each other, and you're just sitting there. You ever thought about
What?
Stop.
Yeah.
Then what are we?
You're not wrong.
What is
Guys, don't you just hate when you start manually breathing?
Shut up.
No,
Don't.
sometimes I forget to breathe. Like I'll be sitting and then all of a sudden I'm like, I have to like, because like I realize I wasn't like taking in enough oxygen or something.
You need to practice. Have you ever heard of box breathing?
No.
What's that?
You take a deep breath in and you count for
Yourself
4.
in a
So
box.
count to 4 seconds, and then you hold it for 4 seconds, and then you
Exhale for
breathe out
4
for 4 seconds, and then you wait 4 seconds. So
Oh.
in 4, wait 4, out 4, wait 4.
That's so.
I always thought it was like in 3, wait 4, out 7.
Wait. But what's
Like,
I mean, you can do whatever makes you feel good.
I
I
was
guess.
suffocate
the
like a.
purpose of box
was
breathing?
Thank you guys for reminding me that I am breathing.
What's
Box-
the
You're
purpose
welcome.
of the box?
the purpose of box breathing is just to help you like relax. It helps to relax you, and it can de-stress. I like to do it when I'm walking. Yeah.
Very cool.
I
Okay.
don't like thinking about breathing.
Well, you're doing it all the time. I have bad news for
I
you.
forgot how to read time. Okay.
All right, guys. Thank you all. Let me know if you need anything. Bye.
Bye.
Bye.